Okay. Good evening, ladies and gentlemen. In this lesson, we're going to be looking at the photoelectric effect. Now, the photoelectric effect is, for me, a rather important section because it actually proves one of the most fundamental ideas that we have today in physics. All right, so I'm going to get started and I'm going to share everything as usual on my whiteboard and we'll hopefully see how this all goes. All right, give me a second. Okay, so we are looking at the section of the photoelectric effect. Now, the photoelectric effect, I'm going to draw a picture first and then I'm going to write it out for you. But what we find, and it's a phenomenon, is that if you have a piece of metal and you shine light onto this metal, so that this is light over here, we shine light onto the metal, it is possible, because you shine light onto the metal, that the electrons that technically are the delocalized electrons that sit usually on the top of the metal, it's possible to cause one of these electrons to be emitted. So we can have an electron that is emitted or given off. Now, that is what the photoelectric effect is. You shine light on a metal and the metal ejects electrons. Couple of important words that we use that are a little bit, I guess, surprising. When light shines on the metal, we describe the term hitting or shining on as light is incident on the metal. So that word incident is one that you probably have never come across before, but you'll see it in all your past papers. So when light is incident on a metal, that means the light shines on or strikes the surface of the metal. When these electrons are emitted, we sometimes get really fancy and technical and we don't call them electrons anymore. We call them a photoelectron. And the reason that we call them a photoelectron, this is the whole idea behind the photoelectric effect, is that when light shines on the metal, this entire phenomenon actually proves that light doesn't behave as just a wave, but light can actually behave as a particle. And the particles of light are called photons. So since we have a photon striking an electron, when the electron is emitted, it's called a photoelectron. Okay, photo, if you think about the word photography, etc., photo is linked to light. Okay, so what the photoelectric effect is it is, I say the phenomenon, I know your definition says the process, so I'll be good. The process whereby an electron is emitted means given off, from the surface of a metal when light of a specific either frequency or energy shines on the metal. Now, this is very important. With this photoelectric effect where we shine the light onto the metal, we find that only certain frequencies of light will cause this to happen, which is a little bit against the original idea of light as a wave. Oh, just give me a second. Sorry. Somebody has unplugged me and I need to quickly plug myself back in. Apologies. There we go. Back again. Not gonna lose you tonight. All right. So when light of a certain frequency shines on the metal, so not just any light will work, only light of a specific frequency. Now, I want to just quickly pause and take a step back and discuss something that's important with regards to what the photoelectric effect proves. Now, you're going to see that we talk in this section about the duality of light. Duality means two. So if something is dual, it can be this and this. Okay, so the duality of light says that light behaves as both a wave and light behaves as a particle. Now that may sound rather surprising to you. Most of you are quite comfortable with what waves are. Okay, so you know that a wave has a frequency, an amplitude, a period. You know that waves transmit energy from one place to another. We believe that light is a wave because, well, it has so many wave nature aspects. It can be reflected, it can be refracted, it does all of the things basically that waves do. So light is a wave most people are comfortable. Light as a particle basically says that you get a certain package of light. And now these packages of light, I'm drawing them as little cubes, and all of these packages are coming through, and that's your package of light. Now, these little packages of light, we're going to call photons. And I'm going to explain to you why it is that we came up with this idea that light can behave as both a wave and a particle. And I use the word can behave as a wave and a particle, because if we view it, we either see it as a wave or as a particle. What was even more amazing about the photoelectric effect proving that light could behave as a wave or a particle is the idea that then said, well, is the converse true? Does that mean that matter, which is our typical particle, also has a wave nature? And the answer is yes. Fortunately, it's not something that you go into in matric, but it's true that everything around us actually has a wave nature as well. Okay, so I find it a rather phenomenal, like, break down the universe kind of concept. So now I'm going to explain to you why we came up with the idea that light has a particle nature as well. Well, according to the wave idea, if light behaved as a wave and an electron needed a certain amount of energy in order to be able to leave the metal, we're going to call that energy, in fact, we do call it the work function. W naught is called the work function. I'm going to define it for you a little bit later. The work function is how much energy you need in order to cause an electron to leave. So if we imagine, say, for example, that this is where you start and this is the energy that you need for it to be emitted, so this is the work function, you could almost imagine that if light behaved as a wave, all the light that shone would slowly but surely add more and 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 more. Okay, I'm getting there. Energy until finally you hit the work function, ta-da, and then an electron would be emitted, which means that we may have a little bit of a delay. We'd wait and wait and wait and wait, and then off would fly our electron and we'd manage to get enough energy for it to leave. So if we're viewing light as a wave, then the energy of the light depends on the intensity. And the intensity of light is actually what we call its brightness. So with us viewing light as a wave, we effectively say if we shine a bright enough light on this metal, it will cause electrons to be emitted, because brightness and your intensity effectively determines how much energy there is. But we didn't find that. What they found when they shone brighter and brighter lights on is that it didn't make a difference. If we hadn't got above a certain frequency of light, didn't matter what you did, no electrons would be emitted. So what they found out was that it doesn't actually depend, or the energy doesn't depend on the brightness of the light. It depends on the frequency. So according to the particle theory, we come up with the idea that the energy depends on the frequency. And in fact, we now know that the equation for that is that the energy is equal to Planck's constant multiplied by the frequency. You should have learned this way back in grade 10 when you learned about the full spectrum of electromagnetic radiation. You learned that the E is the energy of a photon, and that the energy of a photon is equal to Planck's constant. I'm going to give you all of the values now. Please write them down so that you've got them for later on, because I'm not going to keep giving them to you. Planck's constant is 6,63 times 10 to the negative 34. Please, you don't have to worry about the units at the end. We're just going to pretend that they don't exist for today. And F is our frequency measured in hertz. Okay, so that means that we can actually work out that the energy of the light depends on its frequency. Also, something that was surprising was that it wasn't like we wait and we eventually store up all of this energy before an electron's emitted. When an electron was emitted, it either happened immediately or it didn't happen at all. So the idea that they eventually came up with is that we will have a photon coming in. And our photon, sometimes we even represent it as HF as a photon, that will have a certain amount of energy, where the energy is HF. If the photon, I'm just going to draw them as little particles for right now, they're not technically, we usually draw them as those squiggly lines, but if the a photon strikes an electron, okay, I'm going to draw 3 separate electrons here. Okay, if a photon strikes an electron, it gives all of its energy to that electron. If the energy, so I'm going to say if E, which is the energy of the photon, is larger than the work function, I'm going to give you the definition now. Work function is the minimum amount of energy required in order to emit an electron from the metal. Okay, so if the energy of the photon is bigger than the work function, which is effectively the energy needed for the metal to emit the photon, please, I probably should put in the word minimum so that you guys don't leave it out when you've got it in an exam, because that's not the definition if it doesn't have minimum. If the energy of the photon is bigger than the work function, then what will happen is this electron will shoot off. Because the energy of the photon is more than the work function, you're going to have some extra energy left over, and that energy will be found in the form of kinetic energy. And we refer to it as EK max, because it is the maximum kinetic energy of that photon. Now, I just quickly want to pause here because you're going to see I'm going to bring all of the ideas together in just a second. I've got a question. Ma'am, shouldn't it? Oh, thank you. Sorry, I warned you guys at the beginning. I've got a crazy head today. So this is the energy required to emit. Thank you for correcting me. An electron. Okay, thank you. Good. All right, so the work function is the minimum energy needed. Minimum energy, you can see I've left all my words off. Minimum energy needed for the electron, for the metal to emit an electron. All right, and the extra energy goes in the form of kinetic energy. That kinetic energy is the same as all kinetic energies you've ever dealt with. Kinetic energy is equal to 1/2 mv squared. Very important thing, this m still stands for mass. But now we're dealing with the mass of an electron. And the mass of an electron is one of those sneaky things. It's given on your formula sheet right at the top with all of your constants, but they don't draw your attention to it. So in the exam, they're not going to go and say, calculate the velocity of the electron and use the value for the mass of the electron given on your formula sheet. They'll just say, calculate the velocity. And if you don't remember that this mass of an electron, which is actually on your formula sheet given as ME, if you don't know that this is 9,11 times 10 to the negative 31 kilograms on your formula sheet, you're going to get lost. I always just remember 911 like in America and the emergency number, so it's 911. And then it's not quite as big as Planck's constant, which is 10 to the negative 34. It's 10 to the negative 31. But it's on your formula sheet. Don't memorize it, look it up instead. All right, so what happens here is the energy of the photon has to be big enough in order to overcome the work function in order for the electron to be emitted. If this photon doesn't have a frequency that's big enough, what will happen then is that the energy will quite simply go to either having transitions of electrons within the metal or to make the metal hot. I mean, you've all experienced this. You have sunlight shining on a piece of metal, it gets hot. All right, so ladies and gentlemen, at this point, we're just going to pause. We're going to go to the equation. I'm going to explain the equation in full and how to use it. And then we're going to come back and we're going to discuss a couple of important things, like the 2 things that we usually change, or there are 3 things that we usually change with this. The things that we can change with regards to our light, we can change the frequency, or we can change the intensity, brightness, and we can also change the type of metal, which means we'll change our work function. So those are usually the only 3 things that we really change when it comes to the photoelectric effect. Higher frequency or lower frequency, higher intensity or lower intensity. I'm going to explain exactly what the intensity means in terms of the number of photons just now. And then lastly, what changing the metal will do in terms of our work function. Once I'm done with that, I'm also going to look at 3 graphs. Recently, the photoelectric effect has started getting tested using graphs. And I find that a lot of you really panic when you hit graphs. So we're going to look at 3 specific types of graphs that you're likely to get. Once again, using that skill of rearranging the formula, We did it with our electricity. We're going to now do it with this section as well to make sure that you're able to answer it. All right. Please, can I suggest, I know this is a bit of a weird thing. I'm probably going to take away this picture because that's going to confuse you later. You'll be wondering what the millipede was. Please take a photo if you need everything here. Otherwise, I'm going to clear the screen. All right. Okay, so let's clear all of my drawings. So the formula that you're going to get on your formula sheet says E is equal to W naught plus EK max. Please, when you write down formulas, write them down exactly. I know I have this very bad habit where I don't bother with the brackets max. I don't think they're going to penalize you too much for not having the brackets, but I could be wrong. So I'd rather you just wrote it exactly like that. What we're now going to do is we're going to break down each of these quantities and define fully what it is and how it fits together. So firstly, E is the energy of the photon. So this is the energy of the light particle that strikes the metal. There are two formulas that you could use to work this out. The one is that E is equal to HF, and I'm going to remind you again, H is 6,63 times 10 to the negative 34, okay? I'm not going to go into units again. And F is our frequency. So the energy of the photon measured in joules, okay, measured in joules is equal to Planck's constant given over there multiplied by the frequency in hertz. Please, just something to note with frequency, and I'm sure I don't need to mention this, but you never know, is that if I ever tell you kilohertz, that means times 10 to the power of, wrong, my times is in the wrong place. Let's try that again. Times 10 to the 3. Megahertz means times 10 to the 6. Usually they do kilo and mega. I haven't really seen them doing things where it's milli or micro or smaller things. Usually charge gets smaller, frequency can get bigger. So that is the one equation to work out the energy of a photon. Okay, the next equation that we could use is using the idea that V is equal to F lambda. Now, since we are dealing specifically with light, we're only dealing with light. We may view some of the light as being non-visible light, so we can go all the way into ultraviolet and infrared and ultraviolet, gamma, infrared's on the other side going low frequency, but we're dealing with light, so some people will get really technical here and say, well, V isn't V, it's C if you're dealing with light, okay, but same. And what we can then do is we can say, well, what if we don't give you the frequency? What if we instead give you the wavelength? Well, since frequency is equal to the speed of light over wavelength, I can rearrange this and say that the energy of a photon is going to be hc over lambda. All right, so my energy of a photon can either be determined from the frequency or where this value of C is 3 times 10 to the 8, once again, given on your formula sheet. All of them are there on your formula sheet. Don't ignore that formula sheet and think they didn't give it to you or you were supposed to memorize it. Lambda is our wavelength. And very importantly, once again, they may give you the wavelength in unusual units. So usually you're going to have to convert it to meters. Also, very importantly here, you'll see your frequency and your wavelength are often very small and very large values. So please just, even your energy is very strange values, always check for the times 10 to the power of negative or positive values. Don't ignore that scientific notation. So everything that I've done here in blue deals specifically with the energy of the photon. W naught is our work function. Now, the work function depends on the metal. I probably should put in here that the energy of the photon depends on the frequency. And technically, it also, we could say, depends on the wavelength. Because if you've got a constant V, which is our speed of light, if your frequency goes up, your wavelength goes down. And if your frequency goes down, your wavelength goes up. So I guess we could view that if I instead view it from the perspective that it isn't really frequency, it's actually wavelength, it could depend on either. Something else that I've suddenly realized I didn't mention. When we talk about the frequency, you should know when it comes to light that the frequency of light determines the color of the light. So I'll go through the full spectrum in terms of what the energies are, but quite often if we talk about the frequency being constant, it'll be one fixed color. And sometimes when it's one fixed color, they also use the lovely word monochromatic. Okay, so monochromatic means light of one color. And if it's monochromatic, it also means light of one frequency, which means that all of our photons have got the same amount of energy. Okay, let's move on a little bit. So our work function depends on the metal. Some metals give off their electrons really easily, so they require very little energy to do it. Some of them hold on to those electrons, and you've got to put in much more energy to get the electrons to be emitted. So the work function, remember, is the minimum energy required, I'm writing this again so that I've got it right, in order to emit an electron from a metal surface. Okay, so our work function can also be worked out a number of different ways. Technically, this is work, and work is energy, so it's the minimum energy required. So I can go and say, well, that is also going to be h times by frequency. Okay, so energy or work is always Planck's constant multiplied by the frequency. In this case, this F naught is something special. It is called our threshold frequency. And the threshold frequency, I hope that's right, the threshold frequency is the minimum energy, sorry, the minimum frequency, there we go, the minimum, remember, threshold work function is minimum energy, threshold frequency is the minimum frequency, okay, of the light that can cause an electron to be emitted from the metal. All right. Now, once again, because of this equation that we can use V is equal to F lambda, we may not give you everything in terms of the threshold frequency. There is also a threshold wavelength, although the threshold wavelength is definitely the less popular of the two. And then if we rearrange this, we get W naught is equal to HC over lambda naught, where that over there is the threshold wavelength. And you need to realize that frequency and wavelength always go in opposite directions. So if the frequency was the minimum, the wavelength is the maximum wavelength, or the longest wavelength. Okay, let's be technical. So it's the maximum wavelength or the longest wavelength of light that can cause an electron to be emitted. And quite often, I know I've just said here from the metal, but it's from the metal surface. From the surface of the metal. The last thing that we're going to cover today is something that I know a lot of people get wrong. In fact, I have to rather embarrassingly admit I got it wrong until this year. So we're going to go into details now about the kinetic energy. So the kinetic energy, you hopefully know, is the energy of motion. And the energy of motion, or our kinetic energy, comes from the equation EK is equal to 1/2 mv squared. I've just explained to you that this here is the electron mass, which is very, very small because electrons are tiny, which is 9,11 times 10 to the negative 31 kilograms. All right. Now, this kinetic energy is only the energy between where so in a photocell, it's only the energy for when that electron is immediately ejected. If that electron later goes through a photocell and effectively joins with the rest of a circuit, at that point, it no longer is traveling that fast. Okay, I'm going to show you a picture just now that explains exactly what portion of the circuit the specific kinetic energy applies to. So this applies to, here's the metal, the photon strikes it, the electron is ejected. But if this electron later, so here's our surface of the metal, if we were actually to connect this up to the rest of a circuit here, as soon as it strikes, okay, we usually put in an ammeter here, as soon as it strikes this surface and effectively starts moving through the metal, it is no longer going to be going at that kinetic energy. Then we start dealing with the fact of how much is the resistance of the wire and all of those other ideas. Okay, so the current isn't, the ammeter reading, very importantly, isn't going to be affected by this kinetic energy. I know it's a bit of a strange thing. We all like to think, wow, it's got lots of kinetic energy. The electrons are zooming quick, quick, quick. They're going very fast. Of course, the current's going to go up. I can tell you, the current is not going to go up. The electron or the kinetic energy refers just to the portion from there to there, while that electron is effectively moving either through a vacuum or through an evacuated chamber. Okay, so it's not once it hits the metal. Once it hits the metal, it slows down, normal resistance applies, all of those other things apply. All right, ladies and gentlemen, can I ask at this point, before I clear this, does this make good sense to everybody? Okay, I'm going to assume, let me just quickly, I didn't actually get to see you there, so I'm going to stop sharing for just a second. Okay, does this make sense to everybody? Thumbs up again, because I missed all of that. Okay. Cool, fantastic. So it makes good sense, I think, to most of you. Maybe yes, maybe no. Okay, no, that's enough of you. All right, so let us continue. I'm going to quickly clear everything here, and we're then going to talk about the difference between what difference it makes if you change the intensity versus the difference if you change the frequency versus what happens if you change the metal, which is the work function. Okay, so just a quick thing, both the intensity and the frequency refer to of the light, okay, and the work function refers to of the metal. Okay, so if we have a higher intensity literally means that we have got more photons per unit of time. So higher intensity means more photons. More photons are striking the metal. There's high intensity, here's low intensity, okay? So if we've got, this is high intensity, lots of photons. This is low intensity. And what you would actually see it as in terms of a light is it's a bright light or it's not so bright light. Okay. So if we have a higher intensity, we have more photons. Please be careful. It's technically more photons per unit time. Now, what happens is that each photon strikes an electron. So we have a ratio where all of the energy from one photon gives all of its energy to one electron. So one photon causes one electron to either be emitted or not to be emitted. So we have more photons per unit time. If we only change the intensity and we don't change the frequency, then we'll have more photons per unit time, but they all have the same energy. You don't have more energy or less energy. They all have the same energy, okay? And what will happen is that provided that the energy of the photon is greater than the work function, which could also come down to the fact that the frequency of the light is bigger than the threshold frequency. These two are effectively the same concept. So provided that the energy is big enough or the frequency is big enough, we will have emission, okay? Electrons are emitted. But because we have more photons being emitted, more electrons are emitted. And because more electrons are emitted, we will then have a greater current. And please note this current is detected on an ammeter. So we'll have a greater current, which means a greater ammeter reading. Okay. All right, so more electrons mean even if the electrons are traveling slowly, more of them will pass the point per unit time in the circuit, so therefore you will end up with a greater current reading. Please note, all of this applies for higher intensity. Now, I want to ask you, if you have higher intensity, but your energy is less than the work function, or your frequency is less than the threshold frequency, nothing will happen. It does not matter how bright that light becomes, no photoelectric effect will happen at all. You're not giving enough energy. Now, I draw a really weird analogy to this, and I'm just going to quickly stop sharing. Please don't judge me on this analogy. It's just one. All right. Do light sensors and circuits work on this principle? That's exactly what they do. So when I've got a question that quickly came through saying, if you call off cricket matches, so in cricket, they often get very fussy about when the light is bad enough that you can call off the game. If you have to go and detect how bright the ambient light is, you'd be using something like that that measures the number of photons, okay? Bright light or white light that shines us should have all of the different colors, okay, because white light consists of the full rainbow spectrum, and you'd be able to measure how bright it gets. Now, I just quickly want to give you my very bad, weird analogy. So I always tell my students with this example that imagine that okay, now some of you may actually be able to live with this. With us having had COVID, the world has become a very weird dystopian kind of place. So I can give you a crazy example. You live in a world where your entire focus is going to movies. That is all you may do. You may go to movies, okay? In order to go to movies, you've got to buy a movie ticket. And that movie ticket costs 50 Rand. That is the equivalent of your work function. Now imagine I, as the all-powerful money giver, give you money. That money represents energy. So effectively, it counts like a photon. And if I give you 50 Rand, that is going to be enough for you to be able to go to movies. Imagine I gave you 40 Rand. You can't go to movies. But just like the energy from the photon, it either goes to the electron and the electron leaves, or it disappears. It goes into the metal surface and the electron doesn't have it anymore. So if I gave you 40 Rand and you couldn't go to movies, then when I gave you 40 Rand again, you can't go, oh yeah, I've saved the 40 Rand from the first time and I've still got this 40 Rand. That would be that building up idea that I described to you right at the beginning. You can't store energy. So if I gave you 40 Rand, and then I gave you 40 Rand, and I kept giving you 40 Rands, but every time I gave you 40 Rand, the previous 40 Rand disappeared. The outcome is you'd never ever make it to movies, okay? In this case, if we keep giving photons, lots of them, bright intensity, but none of them have enough energy to overcome the work function, then that electron will never ever be emitted. If I were to go completely crazy, so the movie tickets are 50 Rand, and I give you 200 Rand. Now remember, this is a weird scenario where any energy you don't use immediately disappears. I can promise you right now that all of you guys would go completely crazy on popcorn and sweets. You'd basically spend every last cent you were given, because if you didn't, it disappeared anyway. So what happens here is that the energy which isn't used overcoming the work function, which is the paying for tickets, effectively becomes your kinetic energy, which is the buying sweets and popcorn and all the rest. But the idea is it doesn't matter how many times I give you an amount that's less than what you need to go to movies, you'll never ever be able to go. All right, I'm going to come back to this bad analogy just now. Hopefully it'll still make sense. All right, so when we were talking about the frequency, okay, there is a symbol for photon that isn't the shorthand. I think it was phi, but I actually stand to be corrected. All right, so I think that the shorthand for a photon might be phi, but I don't typically use it. I know that some schools and some teachers do. I don't see the point in really using it. We use HF in chemistry, which is why I care about HF, but so that's a chemist symbol. I'm sure that the physicists have got their own little symbol that they use. Okay, if your teachers taught you one, by all means go with it, but there isn't anything else that we expect you to have or that commonly gets put on memos or things that you're supposed to know about. Okay, if we now look at the frequency, you need to know that the frequency depends on the color. Now I want to quickly just run you through the colors, and I may in fact actually draw you a little picture. So over here, the brightest color that you can see in terms of frequency, the highest frequency, is violet or purple. Okay. From there, okay, so I'm just going to quickly write here that this is a high frequency. We did look at this briefly a little while ago. So I'm going to go from high frequency to low frequency. Sorry, pen keeps moving itself. So if we then go through this, we'd have violet, then we'd have blue, then we'd have a green, then we'd have a yellow. Let's try and check that I've got all my colors in order. Then we'd have an orangish color, then we'd have a reddish color. Okay. Anything that is above violet, first of all, is ultraviolet, and then is gamma. I've missed one. X-ray. I missed one. There we go. So we've got gamma, we've got X-ray, gamma, then X-ray, then UV. Gamma is the highest energy, then X-ray, then UV, then all the colors. Here we've got infrared, then microwaves, and then radio waves. Okay, so usually you're going to find that if the color that you've got doesn't emit an electron, you go to a higher frequency. All right, so the frequency of the light, the higher the frequency, let's try and get that all in. The higher the frequency, the more energy the photon possesses. So if we look at the equation, E is equal to W naught plus EK maximum. The idea here is if we increase the frequency, since E is equal to HF, increasing the frequency will cause an increase in the energy of the photon. The work function doesn't change unless we physically go in and take the one metal out and replace it with another. So the work function does not change. So if we increase the frequency, it increases the energy of the photon. This stays the same. This is bigger. So this is the idea of, imagine instead of me giving you, as we said, 50 Rand, which is just enough, I gave you 200 or 300. What would happen is the cost of the movie ticket, the cost of the work function wouldn't change, but your kinetic energy would. So the work function doesn't change, but the kinetic energy increases. Now remember, I explained to you that the kinetic energy increases only while it's in that free flight. As soon as it strikes the metal, it goes back to a circuit, and the rate at which it moved doesn't change. So the kinetic energy increases, but, and this is a huge big but the current in the metal, or in the metal or conductor, let's not go with metal, the current, if I say metal, you're going to confuse it with the rest of it. So the current in the circuit does not change. I know that this is a little bit of a confusing idea, but please just accept that it doesn't change, and therefore the ammeter reading does not change. Now, what has caused a huge amount of confusion with this particular concept is that in 2015, one of the memos accidentally said that if the frequency goes up, the ammeter reading goes up. And I know that that's where I fell apart a little bit, because I learned that very happily, because it made perfectly good sense. Kinetic energy increases, you're like, fantastic, charges are moving faster, therefore the current will go up. But it doesn't happen. It's only during that time of flight between where the metal is and where the anode is that current actually will be, well, that movement of charge will be faster. As soon as it forms part of the circuit, I think there's something called drift velocity, which determines exactly how fast the charges can move. Electrons moving through metal move incredibly slowly. You've got to remember, when we look at the equation that says current is equal to the amount of charge per unit time, that tells us how many charges pass a point, not how fast they're moving. Most of them actually move at a really slow pace. I remember, and I stand to be perfectly corrected on this, but it's still in the right kind of scale. I remember it being something silly, like 4 centimeters a minute, like really that slow. That is how fast your electrons move. Okay, so while the amount of charge is a lot, the actual speed at which they're moving when they pass there doesn't have to be huge. Okay, all right. So hopefully the idea of intensity makes sense. The idea of frequency makes sense. I'm going to quickly cover work function, then I am going to give you a chance to stretch your legs. So the work function depends on the type of metal, and it effectively deals with how much energy is required to cause or allow an electron to be emitted. Now, if we change and use a metal with a different work function, E is equal to W naught plus EK max. So let's pretend, just for an example, that we replace a metal with something that's got a lower work function. If the energy of the photon remains the same and less energy goes to overcoming the work function, then our kinetic energy will increase. Imagine going back to that example, but suddenly now movie tickets are on special. It's a 25 Rand movie ticket. If I still gave you the same amount of money, you would be able to get more sweets and popcorn, okay? So if we have the same photon striking a metal with a lower work function, less energy will have to go to overcoming the work function, so the kinetic energy will increase. Now, please, this assumes that our work function was already, or our energy of our photon was larger than the work function. All of the statements I've made this whole time assume, before we even begin, that the basic premise of the photoelectric effect has been respected, and that's that the energy of the photon is big enough to cause an electron to be emitted. So we could also do this from the other side, and I'm going to do it in a different color. If the work function increases, that means we physically take out the metal and put in a different metal with a higher work function. If you use the same photons and you shine the same photons, the same frequency of light on it, you will end up with a decrease in your kinetic energy, provided, of course, that the photon's energy is still bigger than the work function. So you're still able to get that emission of an electron. All right, ladies and gentlemen, we've been going for 50 minutes now. I'm going to quickly stop sharing all of this. I'm going to clear it, and I'm going to give you a chance just quickly to stretch your legs. All right, so just quickly, can I suggest that you stand up and you stretch your legs, okay, because we've got a little bit of time to still go. Now, I just quickly, while I'm waiting, I want to quickly check out. There was something I wanted to show you, and I'm hoping that I've got it over here so that I can show you quickly. Nope, no such luck. Give me a second. I'm going to have to quickly go and find it. So this is a simulation that many schools use to show exactly how the photoelectric effect works. I'm going to share it with you in a second. Don't worry, I do know I haven't yet shared it with you. I just quickly got to download it because I thought I had it. I'm hoping it's going to work now. Let's hope. Okay. That point where you realize that you haven't downloaded what you already had to in order to be able to do it. So let's just quickly hope that thing opens. All right, while I'm waiting for it to open, I'm going to carry on with the rest of the work that I'd hoped I'd share with you today, and we'll come back to it in just a second. Okay, can I quickly, before I go on any further, actually that's probably a smart idea, can I just double check, is everybody still with me? Does everybody kind of understand, or is it making better sense as to how all the different parts fit together in terms of, I guess, making logical sense of what we've done? All right, that is fantastic to know. Yay, and my simulation's ready. Ha. All right, so let me quickly just share. All right, so this over here comes from PHET, which is one of my favorite simulations because it's free. It's an amazing thing run by the University of Colorado at Boulder. And the story apparently goes that somebody won the Nobel Prize and they accepted a place at the university under the assumption that they were never going to work again. They were just going to create simulations of physics concepts and share them with the world. So if you ever need to find a simulation, Google PHET. Some people call it FET, I go with PHET, it sounds silly. All right, so here we can change the intensity of the light. Now hopefully you'll be able to see this, and hopefully you all can see it, that as I make it brighter, we can have this low intensity to high intensity. High intensity in this case, they say, is 100%. I can also change the frequency by moving the light up or down, okay? over here, you can see how fast the electrons are moving from one pole to another, and you can gradually later on see the measure of exactly how much current is flowing. The point that I want to make here is, let me go down to a really low value. Okay, so I actually want to reset this. I can't, so I'm just going to have to wait for those silly electrons to go through. But if I'm shining right now, those are old electrons. They're not the ones we're looking at. If I look at these old electrons over here, in fact, maybe I should, no, it's not going to make them go any faster. Okay, so if I shine red light, it doesn't matter how high the intensity is, low the intensity is, how long I wait, no new electrons are going to be emitted. So I've got to keep raising the frequency until we reach the threshold frequency. Now, the threshold frequency is where electrons just start to be emitted. So I would probably say somewhere thereabout in the turquoisey color is where I need to start the lowest frequency that sodium will cause or will have electrons emitted. You will notice even within these electrons that some of them move at different speeds. And I'm not talking about the slow pokes here. If I were to keep raising this up, you'll see that we get a range of different speeds at which they move. If I make the frequency higher, we will see that what happens is that the kinetic energy increases. The number doesn't usually increase. If we've got 100% intensity, it should still be the same. But what you should start seeing here is that the kinetic energy gets more and more and more and more. Okay, so if we've got a high frequency, lots of electrons are being emitted. Once the electrons hit here, though, please note they travel at the same speed. So here, my current probably isn't going to change. Well, here it's lying. It's saying it is. So we're just going to not look at that. All right. So over here, this is just a little picture to show you the light, what the intensity means, okay, as well as what the different frequencies mean. Okay, so frequencies are your different colors. All right, we could also do examples where we only show the highest energy. I mean, you can see there's a slowpoke. That guy's definitely not doing his EK max, he's doing his EK slow, but the point is we can calculate it for the kinetic energy maximum. All right, so please, you're welcome to go and play with that simulation anytime you want. I just find it's an interesting one to show the ideas of what it is that we're looking at. Okay, now the next thing that I wanted to share with you was the graphs. Okay, so here's what we were discussing a little bit earlier. This over here is a picture showing a photocell. So with a photocell, we have the metal over here. We've got light shining on it, electrons being emitted, accelerating from the metal to the other side. Usually we've got an ammeter. We do have a battery or a cell in here. That battery or cell is to make sure that this is a positive end, so the electrons race towards it. But the photoelectric effect occurs even if you don't have the rest of the circuit. You can see the photoelectric effect on an electroscope. I'm just quickly going to do a side note here. If we have an electroscope, and an electroscope is something that measures charge, if you have an electroscope, okay, you'll have a piece of metal rod that goes down. And down the side, I'm going to make it orange. You've got a little thin leaf of gold down the side. Okay, so this would be inside the container so you can't see it, but this over here is metal. All right, so sorry, not so you can't see it, it's a glass container, but the metal sides. All right, so over here we've got a disc. All of this is made out of metal the whole way, and that's your little gold leaf electroscope, little piece of gold leaf. Now, what happens is if we shine light onto here, I shouldn't probably have used red, I should have used another color, and it causes electrons to be emitted. Oh, that's a bad color for electrons to be emitted, and it causes electrons to be emitted. What will happen is that this will gradually become more and more and more positively charged. The metal will become positively charged, and the gold leaf will become positively charged. I'm regretting drawing the gold leaf in. So what will happen is the gold leaf will be repelled from the surface. Everything here is positive. The gold leaf will be repelled, and you'll end up with those two repelling each other, because the gold leaf, it's a thin, thin, thin layer of gold, is so small and thin and lightweight, it just gently flips up. And that over there can tell us that electrons have been striking here. We could also do it the other way around, where we start off with this being negatively charged. We shine light at the right frequency on it, and since it was negative, as it loses the electrons, it becomes less and less charged, and this little piece of gold leaf moves down. So it is possible that they can look at gold leaf electroscopes. Will you ever be asked the electroscope in an exam? Yes. I don't know if it's going to come up in your exam now. I do note that somebody recently mentioned something to me that made me think it might. Okay, not that they'd necessarily have insight into it, but just that they said that it hadn't been included in certain notes and therefore it should be covered. So I'm not certain when it becomes relevant, but I think it's very important that you are aware of the fact that we can use just a simple electroscope to show the photoelectric effect. Usually, though, it wouldn't be good enough to just use the metal. We'd actually put our own piece of metal onto here to shine the light onto. So you'd put your own piece of metal on the top. Because everything's metal, the electrons can comfortably move or be conducted between all of them. This is the exact formula that you're given on your formula sheet. So it basically says E is equal to W naught plus EK max. Please, as always, if you are English, avoid the Afrikaans in terms of letting it or getting it to confuse you. Sometimes it really helps if you don't understand what a question means and you're pretty fluent to go through and actually read the Afrikaans version of the paper, because all of you in your final exam will get a dual medium. Once again, dual, there's the word dual. So you'll get an English and Afrikaans paper. You can go and use it to check. But this is exactly what you'll be given. So they kind of break everything down for you, but they don't tell you what Planck's constant is. You've got to look that up on the very top of the formula sheet. And they don't remind you that this is the mass of an electron. You've got to look that up as well. All right. Now, I mentioned to you that I was going to go through graphs with you. And I think graphs will probably take us to the end of today's lesson. So let's have a look. These are the different graphs. And I actually want to show you how we get to all of the conclusions that have been raised here about what the gradient means, the y-intercept, etc. So I'm going to start off, as I always do, with E is equal to W naught plus EK max. All right. Now here we're going to plot kinetic energy. That means that this is my Y value against F. Now this F is the frequency of the photon. So it is referring to the F contained in E. So I have to then take E and say E is equal to, let's do that slowly, HF is equal to W naught plus EK max. All right, so now I've expanded my formula just enough for me to be able to see all of the variables. I want this to become my X value and this to become my Y value, because we're going to try and turn this, I don't know what I'm writing there, into the equation Y is equal to MX plus C. So if I do that, I'm going to take EK on its own and I'm going to get W naught to go to the other side. So I'm going to say EK is equal to HF minus W naught. All right. Hopefully everybody followed that I just flipped everything and moved things over at the same time. So the kinetic energy is now on its own. The W naught went across to the other side and changed its sign. So this is now Y, this is now X. That tells me that Planck's constant is my gradient and my C value, which is my Y-intercept, is negative work function. This kind of does make sense because your work function is in joules. So anything that's measured on this axis has to also be in joules. So over here, if you know your Y-intercept, you can then immediately say whatever this value is, that's going to be negative my work function. The gradient is going to be Planck's constant, which I might reiterate is a constant, which is why it is going to be a straight line. So the straight line tells us that it's a constant, nothing's going to change. So whatever it is has to be something that doesn't change depending on the frequency. And lastly, my x-intercept has some significance. Now, I'm not going to rearrange this equation to solve for F naught by saying something along the lines of let EK max equals 0 or anything unnecessary like that. What I want us to do is to just quickly go into the idea that if you've got a negative kinetic energy, no electrons can be emitted. The entire space here, basically what it's saying is that the frequency is too low for electrons to be emitted. As soon as we start getting a kinetic energy, even if we're dealing with the technical, very unusual thing. If you think about this practically, just for a second, if your energy of your photon is exactly equal to your work function, the electron is emitted, but with no kinetic energy, which means it leaves, but it doesn't leave with a velocity. Those of you that are good physicists or overthinkers will have a very big problem with this, because you can't leave if you're not going. But we're prepared to say it leaves, but with no kinetic energy. So at this point, this is effectively the minimum frequency for electrons to be emitted. Even if they're emitted, that should be a B, emitted, even if they're emitted with no kinetic energy. After that, if we give them more energy than they need, so if we've got a big enough kinetic energy that our work function's covered, then we're going to have more and more and more kinetic energy, which is what happens over there. Does this particular layout now make sense to you in terms of what this particular graph means? All right, I'm going to quickly stop sharing so that I can just double check. Everybody's still with me? Okay, fantastic. All right, back to the next bit. Okay, so that was our first one here. Okay, first graph. Sorry, I didn't give you a chance to screenshot it. I unfortunately shifted and it doesn't allow me to go back. So I'm going to have to watch the video and take a screenshot later. The next one that we've got over here is a similar graph, I guess, where we're now looking at the kinetic energy against 1 over lambda. So what I'm going to do here, I'm going to write this down a little bit towards the bottom, is that I'm going to start with E is equal to W naught plus EK maximum. Then what I'm going to do is I'm going to say, well, I've got 1 over wavelength, which means that I've got to bring in the equation over here that says E is equal to HC over lambda. That is equal to W naught plus EK maximum. I hope you're all getting the hang of this, rearranging the formula and bringing all the parts in. Now, I need to get the kinetic energy on its own because it's my y-intercept, so the W naught needs to go across. So I'm going to say EK maximum is equal to, I'm going to start splitting this here, HC multiplied by 1 over lambda, not plus, let's go back one step, minus W naught. So I'd like to check, do you all understand that the work function got moved over and became negative W naught? And all that I did here was I split this up, where I said, all right, cool, look, there's a 1 over there, and I'm taking out that bit as 1 over wavelength, and then there's an HC being multiplied by it. So if we now look at this in its parts, that is my Y value, this is my X value, that is my gradient. Once again, constant, constant. So both of those are constant, which means that our gradient is also going to be constant, which is going to give rise to a straight line. The gradient isn't going to change. And then here, once again, we've got a negative y-intercept, which is going to be negative the work function. So if you work out exactly what that value is, that'll tell you the work function. And over here, your y-intercept is going to effectively tell you over there your threshold wavelength. Okay, so that'll be your threshold wavelength, and we can work around this. Now, as always, this version is not highly likely. I am hoping against hope that as much as they say your final exam is set and cast in stone, that they are going to bear in mind just a little bit that you guys have had a bit of an upheaval this matric, and they're not going to be asking you these ridiculous versions like this one. But just in case, I think it's worthwhile that we prepare you for the absolute kind of craziest version of what they can give you. All right. Okay, so that was the next one. Let's quickly clear this. I'm going to scroll down to the last one over here. All right, now this one's a little bit unusual. So let's have a look. E is equal to W naught plus EK maximum. Now, if I look at this, I have got E, which is fantastic because that's already my Y. But they've also got V squared. So I'm going to have to split up my kinetic energy maximum to get that out. I'm going to have E is equal to W naught plus a half mv v squared. Now, if I am plotting this as my y and this as my x, and using the formula y is equal to mx plus c, I'm going to go and say E is equal to, I'm going to have a half m times by v squared plus w naught. The reason I rearranged that is I want to have y is equal to mx plus c. Please note that my gradient is a half of the mass. So the gradient here is the half of a mass of an electron. Mass of an electron is 9,11 times 10 to the negative 31 kilograms, which is a constant, which means we're going to have, again, a straight line. The y-intercept is a positive this time. It isn't minus w naught, it's a positive, and that over there is your work function. So this effectively says you've got to get to this amount of energy before we'll have electrons being emitted with any velocity. After that, if you give us extra energy, they'll leave with extra velocity. All right. So here you can see another version. What they'd usually do if they gave you something like this is they'd give you the graph, and then they'd ask you without spoon feeding you. So they're not going to tell you, look, this is what the gradient means, and look, this is what the y-intercept means. You'd quite simply be given a graph that had energy against v squared. You'd maybe get given a specific value here. I don't know what it would be, but whatever it is. And then they may ask you to determine what is the gradient, what is the y-intercept, possibly even reading off the graph if you use a certain frequency, which you'd then have to take frequency to get to energy, and then they'd say what is the velocity at a certain point, something like that. So they're going to ask you quite a lot of reading between the lines and reading around things. All right, ladies and gentlemen, please take a screenshot of that if you still need us to go through it. Well, if you need to check later. All right, I'm going to quickly clear all of my drawings, and then I'm going to stop sharing for just a second. All right, can I quickly ask at this point, who understands everything that we've done today? Give me a thumbs up if that's the case. Okay, there are a few of you who don't, but that's a good sign. All right, I hope that this makes really good sense to you. This section I find to be a really nice, in a nutshell, quick one. Now, just to give you an idea of what we're planning on doing for the time going ahead, is I'd like very much when I see you on Thursday for us to go and do a lot more past paper questions on this, because I think today we've covered most of the theory. There is a little bit that I haven't yet done with you on the absorption and emission spectrum, although I did cover it when we did the Doppler effect. So please, if you haven't yet done that, go back over the videos of the Doppler effect, because we are going to be applying the absorption and emission spectrum. But I hope that what we've done up until this point makes good sense to you. All right.